Hey guys, we are on the penultimate lesson of this unit. I sorry, I got distracted because I realized last time I was making these or I was uploading one of these videos that at the beginning of every video I have to situate myself and mess with my thing. I don't know, just is that's how I'm rolling right now. I don't know what's going on. But we're going to be talking about relations and I've already hemmed and hawed enough, so let's go ahead and dive in. All right, so we're talking about relations. So we're talking about how we're talking about a relationship between sets of data. Okay, so we're talking about sets of data. Okay, so we're talking about sets at this point in our life, at this point in our math life. We're talking mostly about lists of numbers. Lists of numbers, right? And for relations, we're talking about how one set relates to another set of numbers. And that's really all there is to it. There's several different vocabulary not words, but ideas that we're going to be discussing. Let me bring up a grid real quick. Okay, so let's get some vocabulary out of the way. So, first of all, this whole schmagoigle right here is called a coordinate system. Coordinate system. It's actually, if you want to be really technical, it's actually called a Cartesian coordinate system, named after Descartes. I can't remember what Descartes' first name was. I believe he was a French mathematician, but I could be lying. But there's your trivia for the day. So this is all called a coordinate system. Each one of these lines here, so like this one and this one, are the axes. Let's see. I should actually let me switch colors here real quick so we can have things nice and neat and clear. So these are the axes. I'm gonna label the yellow as axes. 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 This horizontal axis, the horizontal one right here, is the x-axis. And this vertical one right here is called the y-axis. This is by convention, not necessarily rule. You could actually label these however you wanted to label them. In fact, once we get into doing this in science classes or statistics classes or any of those things, then they're very often labeled something else. Like this x-axis might actually be the time axis, and the y-axis might be the velocity axis, or the y-axis might be the items axis, and the y-axis might be the cost axis, etc., etc., etc. But we're talking about generic math problems. The horizontal axis is the x-axis, and the vertical axis is the y-axis. Now, if we want to describe a particular dot on the axis, so say we wanted to describe this dot, we do it with an ordered pair. Okay. Now, you may be wondering, okay, so we're calling this a relation. We're talking about a relation. So in this very, very limited example, we're talking about a relationship between a number on the x-axis with a number on the y-axis. So this particular ordered pair, if each one of these lines, we count one, this is the positive x-axis. So this would be 1, 2, 1, 2, 2. 1, 2, 3, 4, 5 over, right? And this is the positive y-axis. right? So we went up 1, 2, 3, 4. So this ordered pair right here would be the ordered pair 5, 4. So when we list an ordered pair, we always list them as the X, comma, the Y. Right? So let's put a couple other ordered pairs on there and see if we can kind of make sure we understand what's happening. You've probably seen this before, Algebra 1, but if not, I want to make sure you have all the notes that you need in order to get make this happen. So let's put a lead. Let's put a red point. Let's put him right here. Now, if this is the positive x-axis going to the right, then the negative x-axis is going to the left, right? So we went -1, -2, right? So this point right here is the point -2. So we went back 2 to the left 2, comma. Now we put the y part. Now we went up 1 point. So -2, 1. That's easy peasy. Let's do 1 in every quadrant. Each one of these boxes is called a quadrant. All right, let's do an orange one down here in quadrant 4. So where would this point be? Right? This point we counted over 5, 6, 7 on the x-axis. +7 because it's to the right. But now, if up is positive on the y-axis, then down has got to be minus or negative. It doesn't look right because that crookedness doesn't look right. There we go. So this is negative y-axis. So we went down 1. So 7, comma, -1. Easy peasy. Let's do we've already got yellow. We've already used green. Let's move on to this turquoise color. Let's do one. How about right here? Looks like a great place. So what would this one be? This one would be -2, back 2. And we went down, so it's also negative. -2, -1, 2, 3, 4. -4. Okay, so that's how we look at a point and we label that thing as ordered pair. You've probably already seen that. All that's probably true and all those things, but just as a means of really quick review in case you haven't seen it, there's all of that. Now, let me kick that off. The next vocabulary word that we're going to use is the word mapping. Oop. I need somewhere to write. Is that something? Yes, that's something. Okay, I need somewhere to write. Here we go. Is mapping. All right. So we might have a relation that looks like this. We're going to draw a bubble diagram. We're going to list some numbers in a bubble over here. We're going to list, in this one, we're going to list -2, 1, 5. That sounds great. So we've got a set of 3 numbers over there. And we've got another set over here of the numbers 2, 4. Okay. So if we are going to map these numbers onto those numbers, this is how we do it. We draw arrows. So I could say that this number maps onto that number. So -2 maps onto a 2. 1 could also map onto the 2. And then the 5 could map onto the 4. Right? So this is kind of the fundamental start of talking about a relation, right here is if we have one set mapped onto another set. So this right here, mapping kind of makes a relation happen. This isn't quite true, saying mapping equals a relation. That's not quite true, but it gets the idea strongly enough that we're gonna leave that idea right there. Okay, so now we have, you notice we have two sets, one set related to another set, hence the word relation. So let's kind of draw some more organized bubbles, because we're gonna talk about some different things. I'm going to even add some more generic, well, it doesn't really matter, actually. Let's keep it numbers. I was going to say let's put letters or something, but as I thought about it, that might be confusing uselessly, because in this context, it doesn't really matter. So let's have a set with 0, 1, 2, 3, and then another set with -5, -4, -3. How's that sound? Sound great? And then we're going to map it, which makes it a function. It doesn't make it a function. We'll talk about that in the next lesson, what makes a relation into a function, but it does make it a relation. Map a 0 onto a -5. We're going to map a 1 onto a -4. We're going to map a 2 onto a -3. And we're going to... that's weird. Oh, I see. I understand why it's weird. We're going to map the 3 also onto the -3. That sounds fine. So on this left side, we're mapping these, and they're pointing to these other ones. So what we call this left-hand side over here, we say that these are the domain of this relation. And then over here on the right-hand side, this is the range of this relation. For our example, the domain here would be 0, 1, 2, 3. And for our example right here, the range would be -5, -4, -3. So that list of numbers that is in this left-hand side, and we're going to put some other words on it here in a minute, is the domain. Then this list of numbers is the range, okay? Now, the domain on our grid that we'll talk about again here in a minute, the domain relates to the x coordinates. So this would be a list of all of the x's. The range is associated with the y coordinate. All these are the list of the y's. Now, if we were to rewrite this map as a list of ordered pairs, then we would take and look at our mapping. So if we listed this way, we would start with the ordered pair 0, -5. 0, -5. The next ordered pair in this relation that's our example, should put example, right? Okay. It would be 1, -4. And the next ordered pair in this example would be 2, -3. And then the last one would be 3, -3. Okay. So this is two different ways that we could represent this exact same relation. There are actually several different ways, and I'm gonna show you how to represent a relation in different ways by looking at an example. Okay, so we're going to pull up our grid because we're going to need it, and I want to make sure I'm not accidentally writing on it. And so let's do, I know those were examples. This is official example 1. Example 1. We are going to express we're going to write out a relation as a set of ordered pairs. This is a curly bracket. A lot of times we put sets inside of curly brackets. Okay. And so ordered pairs. So the first ordered pair is going to be 2, 5. The next ordered pair is going to be, let me shrink my pen down a little bit. Next ordered pair is going to be -2, 3. The next ordered pair is going to be 5, -2. Because of my space, I'm going to keep on writing this on the next line. And the last ordered pair is going to be -1, -2. So we're going to express this relation as a table a graph, and a mapping. All right. So this is super easy. We got this. We got this, folks. It's not going to be that big a deal. So for the table, this is what you do. We're going to do kind of a T-chart table. We're going to list X, Y. We're going to go, keep forgetting that I'm on this program and can draw straight lines without having to think hard. We're going to draw a T-chart, and then we're going to list all these things. So 2, 5, 2, 5, -2, 3, 5, -2, and -1, -2. So there's the table. Done. Wow, that was hard. You got this. No problem. And then as a graph, so we're going to graph it. I'm going to just label graph in red for notes' sake. Right? So we're going to graph 2, 5. So over 1, 2, up 1, 2, 3, 4, 5. Then -2, 3 would be back 1, 2, up 1, 2, 3. Put a dot. Blammo. 5, 2 would be over 1, 2, 3, 4, 5, and then down 2. Down 1, 2. So we put a dot. There it is. And then finally, -1, -1, 2. Graph. Also easy peasy. And then a mapping. Let's do a mapping. We'll do that one in this nice pretty blue color. Okay, so we're going to do a bubble with all the X's in it. So I'm going to list them first and then draw my bubble. 2, -2, 5, -1. So there is my domain. Gosh, that's awful. That's not much better, but it'll work. And then my range is 5, 3, -2, -2. And then I'm going to map it. Go back to that orange color we were using before. So 2 maps onto 5. -2 maps onto 3. 5 maps onto -2. -1 maps onto -2. Easy peasy, lemon squeezy. We got one more little set of vocabulary words, kind of, and then a couple of simple examples with it, and then this video is all through. All right, so let's hide this, hide that. So we said, excuse me, we said that the x's are the domain. X also has another name. It is the independent variable. I never can remember if it's int or ant. It's int. Independent. I say it right, but I always trust myself. You know, West Texas, we sometimes struggle with that. And then the y, if is the range, right? It's the dependent variable. Okay. Now, the easiest way to think about this is the way it sounds like. And we're going to, when we're talking about independent and dependent variables, a lot of times we're talking about word problems. And so this can be a really useful way to figure out, and we're going to deal with lots of different things and how to graph stuff and all kinds of crazy things as we go in the future. But we're just wanting to know which variable to put where in an equation later. But for now, all we need to do is identify which variable is the independent and which variable is unknown is the independent quantity and which one is the dependent quantity. Let's look at a couple examples and see if we can make some clarity on this. So here's the first example. So we're going to look at this example. We're going to read it, and we're going to let me see if I can. Yeah, perfect. We're going to read it, and then we're going to look at it and identify what the unknowns are and which one is independent and which one is dependent. And the best way to think about it is to think about which one depends on the other one. So let's read it. The dance committee is selling tickets to the fall ball. The more tickets that they sell, the greater the amount of money they can spend for decorations. So let's see if we can figure out what the unknown quantities are, right? So the more tickets they sell, the greater the amount of money that they can spend. So does tickets depend on money, or does money depend on tickets? So which one is independent, which one is dependent? So the more tickets they sell, the greater the amount of money. So money, the amount of money they make, depends on the amount of tickets that they sell. So money in this case is, I don't remember what I did, orange or yellow, which one I did orange, which one I did yellow. So I'm just going to go to our generic white color and say, what did I just say? The money is greater the amount of money. The money depends. So the money is the dependent quantity, and the tickets is the independent quantity. That's easy peasy, right? Let's look at one more of those, and then we'll call it quits. Generally, the average price of going to the movies has steadily increased over time. Now, this one's tricky because it could be difficult to identify the second variable, right? So the average price is going to be one of the variables, obviously, right? But what's the other unknown? This one is a little bit tricky, right? But what it is time. Price is changing as time changes in this problem. So time is the other thing. Now, time is a kind of a special case, and it's special enough that we're gonna think about this one a little bit differently, and that is that time is almost always, pretty nearly every time. I can't think of an example where it wouldn't be. I'm tempted to just say it is always, but then somebody's going to have some weird counterexample that I'm not thinking of for some reason. But time is pretty much always the independent variable. because we can't change time. Time just happens, right? So time is the independent variable pretty much always. Anytime it's one of the unknowns, it's independent, which means price is dependent. In this problem, it makes sense even if you think about it our normal way, because price, the average price, depends on how much time has passed. So either way, price is dependent, time is independent. So those are the types of examples. That's it for this video. Thank you guys for watching. If you're one of my students, you can find homework or any of those things in your assignments pages. And if you are just joining us on YouTube, thanks for being here. Make sure you subscribe and hit that like button. Remember that we have the entire Algebra 1 course, the lectures at least, for free here on YouTube. So we really appreciate your support and hope you get a lot out of it. If you want to see anything else we're doing or find out any other things that we offer, you can head over to emberlearninglabs.com. Thank you guys and have a grand and glorious day.